Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to graph a quadratic function in factored form. That's our goal for today, to graph a quadratic using its zeros, and we're also going to learn a little bit about what the axis of symmetry is in quadratics. And you're successful, of course, when you can sketch a quadratic when it's given to you in factored form by using the x-intercepts to find out where is that vertex. To start off, I want you to define the word symmetry in your own words. Although, if you've never encountered this word before, you're certainly free to look it up. Well, if I had to define symmetry in my words, let's compare your definition to mine. I would say it's sort of like the idea that half an image is a mirror image of is like, almost like a mirror of the other half. So, for example, let's take a look at this astronaut. Is there anything symmetrical about our friend here? See if you can point out anything, and then we'll resume and pause the video and think about that, and we'll resume in a minute. When I look at this astronaut, I say that yes, there is a lot that is symmetrical about them. For example, if I draw a line right through the center of the spacesuit, most of the items on the left are almost like a mirror image of the items on the right side, except for this tube and the center thing. Almost everything seems like it's like this red line is a mirror for the left and right side. And so let's think about this for a little bit. For example, which blue button with these two buttons, which ones do you think is actually closer to the center? Actually, I would say that these are equidistant. So equidistant means that they are both the exact same distance. Look at that. If I move that arrow over to here, notice I touch the blue button on the far side and I touch the line closer to the center. A line in math is sometimes called an axis. And for this reason, we'll learn today about an axis of symmetry, an axis that creates this mirror image. Before we do so, let's take a look at one other question here. Which of these white buttons is closer to the axis of symmetry here? I think hopefully you're able to come to the same conclusion that I am, which is that they are also both equidistant. And that's the idea behind an axis of symmetry. If there's an object to the left of the axis of symmetry, there will be the exact same object to the right of it, the exact same distance away as well. Now to relate this back to mathematics, I'd like you to pause the video here and take as much time as you need to graph the roots and the vertex of this function. Well, let's start with the roots. So I need to know what value of x makes this factor equal 0, and what value of x makes this factor equal 0, and those will be my two roots. Let's focus on this one first. So I've got adding 2 to the side to get rid of the subtracting 2. That'll cancel it out, and then I have to change the other side of the equation as well. And I find out that one of my roots is x equals 2. The other one, if I subtract 4 from both sides, I find out that x is alone on this side now, and 0 minus 4 is negative 4. So that's my other root. So I'll put 1 at 2 and 1 at negative 4. Now to graph the vertex, that's a little bit harder. So if you were only able to graph the roots, then you can pause the video here and do this next question, which will help you graph the vertex. We can't really do that just yet when we have it in factored form, but if we converted this to vertex form, we certainly could. And to do that, we have to actually convert it to standard form first. So pause the video here and see if you can convert it to standard form. And if you're able to continue to vertex form, that's great. Well, let's do this. To convert anything to standard form, we just have to expand and simplify. So let me just expand my binomials first by using FOIL. Right? That's x times x plus x times 4 plus negative 2 times x plus negative 2 times 4. That gives me this resulting equation or expression, and I can combine these two like terms to just get x squared plus 2x minus 8. Now I can't forget about that 3, so I'm just going to bring that back here now. Okay, we're not quite at standard form yet. We still need to distribute this 3 to all 3 of these terms inside the brackets, and that right there is my expression in standard form. Now let's convert it to vertex forms. And I do that by completing the square. So I'll factor the a value out of the first two terms. I'll take this coefficient now, divide it by 2 and square it to get 1. And then I'll add and subtract 1 inside the brackets. Now to move this -1 outside of the brackets, I do have to multiply it by 3. So I'll do that now, right? And that gives me -3. And now this is a perfect square trinomial, and these two are like terms that can be combined. And there we go. That is the vertex form of this quadratic. And that can tell me very easily that the vertex is going to be at -1, the negative version of whatever this number is, and -27. And I can plot that out here. So that's -1. There's -27. That vertex will go right over there. And now that I've got the two zeros and the vertex, I know that this is the tip of the parabola, so I can very easily just draw a very smooth curve through them. And that's one way to graph a quadratic if you're given it in factored form. You could just graph the zeros, expand it to standard form, complete the square to get it into vertex form to get the vertex. And once you've plotted the vertex, you can draw that smooth curve. I'll give you one last try, one more chance to do this exact same process. Do the same thing with this function. Pause the video here and graph the roots and the vertex. Okay, well, hopefully you were able to, recognize that very easily. One of the roots is +2, and the other root is 4. And I didn't even really need to do this to find that out. So I'm going to plot those two right there, 2 and 4. And now let's convert this to standard form by expanding our brackets here using FOIL. Combining our like terms, and then finally distributing that a value to all three of these terms to get this function in standard form. Then to convert it into vertex form, we complete the square. So let's factor out a, take the coefficient divided by 2 and square it, add and subtract this number inside the brackets, and then move this -9 outside the brackets by multiplying it by 6 to get -54. Now that's a perfect square trinomial, which will always be x minus half of this, so x minus 3 squared, and 48 minus 54 is -6. So my vertex is going to be at 3 and -6, which is right there, 3 and -6. And now I can connect those with a nice smooth curve. This process seems to take quite a lot of calculations. There's lots of room to make mistakes and stuff. So let's complete our investigation here. To do that, let's notice that the first investigation that we completed, this function had roots at -4 and 2, and a vertex at when x was equal to -1. And this function had roots at 2 and 4 with a vertex when x is equal to 3. To really understand this and see if you can notice this, draw a separate number line for each of these two functions and plot the x value of the roots and the x value of the vertex. So this is what a number line should look like. Just put maybe a blue dot at wherever you know the roots are, and a red dot where you know the vertex's x value is. If you do that, you should notice something. You should see something like this. So -4 and 2, and the vertex, of course, it was at x equals -1 right over there. And for the other function that was at 2 and 4, those were our roots, and the vertex was when x is equal to 3. You notice anything? Pause the video here and really examine this until you can figure it out. Well, hopefully that idea of symmetry primed your mind for getting the right things noticed. If you notice, the x value of the vertex is always exactly in between the two roots. In fact, if we wanted to find the vertex from factored form, we didn't actually have to complete the square. We can just find the h value just by looking at what number is right between the roots. And the way you would do that is average the two roots. So add them together and divide it by 2. And then once we have that value, you can just plug that value back into the function. So find f at -1. And when I plug in -1 into x over here, you should find out that the y value is -27, just like we did earlier. That's the value of k. That's the maximum or minimum. This is why the axis of symmetry is so powerful and helpful for us. When you have a quadratic function, any 2 points, for example, these 2 points, if they have the same y value, so if they are at the same exact horizontal sort of location, so if one is not higher than the other, then they are always going to be equidistant from the axis of symmetry. Okay, so these 2 points on the parabola, they have the same y value. Their distance from the axis of symmetry is exactly the same. If I had 2 other points over here, they would be equidistant as well. They wouldn't have the same distance as the red point up here, obviously, but the 2 blue points, the ones that have the same y value, they have the same distance from the axis of symmetry. And of course, the best example of 2 points that have the same y value are the roots, right? They both have a y value of 0, and they are both equidistant from the axis of symmetry. So we can use that idea to average them to find out what is the axis of symmetry. In the previous page there, I mentioned that the axis of symmetry, we can just take that value and plug it in to find the y value of the quadratic, and that's true. The axis of symmetry will always go through the vertex of the parabola. So if in this example, if I took 1 and I plugged it into the function, I would find out exactly what this value is. So if we did want to graph a quadratic function from factored form, we don't actually have to expand it and complete the square to find the vertex. First, we'll just graph the x-intercepts. Then we will average them to find out what number is right in the center. What is that h value? Okay, that is the x value that's right in between. That is the x value of the vertex. It also tells us that the axis of symmetry will have an equation, x equals whatever that number is. The axis of symmetry will be right there. Now, if we want to find the y value of the vertex, we just have to plug this value in. So find f at h, and that will give us the value k, and that's the y value of the vertex. So at that point, let's say it's somewhere like, right over here. All I have to do is now graph that point that represents the vertex, and now join all 3 of these points with a nice smooth parabolic curve. One thing I would recommend as you're going through these 5 steps is to try to do all of the calculations before you actually start graphing. And that way you can establish exactly what your y and what your x scale needs to be so that you can get it all on one graph without sort of making your graph too large. For example, if we had to graph this function right here, this is a quadratic in factored form, right? The r value is -2, the opposite sign of this, and the s value is +4. So to graph this function, like I mentioned, the first step is to graph the x-intercept. So that's -2 and +4. We take the average of their x values, so -2 plus 4 divided by 2, and that tells this will evaluate to just 1. And notice that that number 1 is right in between -2 and 4. That is our axis of symmetry. Okay, that is also going to be the x value of the vertex. And because I know that, I could just take 1 and plug it into my function. Find out what is f at 1. This is my function. If I replace x with 1 here, I have to replace it here and here as well. And now I can start evaluating this. 1 plus 2 is 3. 1 minus 4 is -3. 1/3 times 3, or let's just do these two first. 3 times -3 is -9, and that times 1/3 is -3. So that's our k value. F at 1 is -3. So that will be the y value of our vertex. So our vertex, which must be on this line and must be on this line, must of course be right here. So we can graph that point. Now all we have to do is join those points with a nice smooth parabolic curve. And we're done. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.